Thank you very much for the introduction. So good morning, everyone. So yeah, as you just heard, I'm principal engineer at Monolith AI, and today I will explain how we collaborated between Monolith AI and Kistler to look at how we can combine artificial intelligence and historical physical test data to accelerate product development. So to do so, I will start with a short introduction about Monolith AI, the company. Then I'll spend some time introducing you to the platform that we developed, and finally spend most of the time in the use case that we looked at with Kistler. So the company, Monolith AI, created a software that is combining artificial intelligence and your historical data to accelerate product development. It was created in 2016 and has kept growing since, and is working with leading engineering companies, mainly in the automotive industry, but in also other industries such as aerospace or energy. So quite a variety of different industries. And the concept is quite simple. We leverage all the data that you gathered in the past, and we train algorithms on them to be able to predict the behavior of new product and understand better how your new product would behave. To do so, we work mainly with simulation and physical test data. So for simulation data, the platform can learn from kind of conventional tabular data, like a big table, for instance, but also directly from the 3D geometry. Thanks to algorithms that we developed in-house, we can train machine learning models directly on a mesh, for instance. And we can link that mesh and these kind of input properties to the performance of your design, whether it's the drag or the strength, for instance. And the idea here is to reduce the design iterations to get faster to your final design. And for physical test data, it is a quite similar process. This type of data is really expensive to gather, whether it is because of the cost of renting testing facilities, like renting a wind tunnel, for instance, or just because of the cost of prototyping. And so here, the idea is quite similar. We learn from past test data. It could be sensor data, time series, for instance, and we can do what we call rapid prototyping or virtual testing, where we can have a quick insight of what would be the outcome of a physical test without having to perform it. And so here the idea is not to completely replace these tests. We are aware that they are needed, especially for certification, for instance. But the idea is to reduce the amount of unnecessary tests. So being able to find ahead of time which test would not work or how we should change the design to ensure that they work. And here the idea is to reduce the amount of tests required to bring your design to its final certification. So this is about our platform, our company, sorry. Now about the platform that we developed, here I have a schematic that explains how it can be completely integrated within your workflow. So if you start from the bottom here, you can see the typical engineering workflow, where you have your design, the simulation, test, manufacturability, production, all these different kind of steps of your workflow. And so the platform will be able to ingest data from all these phases, whether it is simple Excel file or time series or more complex CAD files, finite elements, CFD, FES simulations, for instance. And they're brought into the platform, where the typical workflow would be to first import this data, then to explore them in a way that is interactive, so you can really understand your data better than sometimes just looking at one plot, for instance. Then we can transform it, clean it, combine it, make it suitable to have machine learning algorithms learning from it. So it might require a bit of cleaning, which is feasible in the platform. Then we have the modeling part, which is the main part of our platform, where we have machine learning models that will learn from this data. And once these models are trained, we can evaluate them, make sure they're good, and use them to make predictions. So predictions, for instance, to find the outcome of a new design, a new geometry, new operating conditions. And finally, when we have these predictions and these results, we can share them. And here we try to really kind of help with the collaboration between teams, within a team, with colleagues, so you can share your results really easily. And the way the platform interacts with the client workflow is through users, which are mainly the engineers, but also data scientists, if you want, and also APIs to automatically connect our platform to the different solutions that you are already using. And the overall solution or the overall outcome of all this would generally be that you either reduce the amount of tests that you're doing, or you might reduce the amount of simulations, or you can improve the design as well, or it might be a combination of those. But that is what the platform will do for you and with your data. So here I have a couple of screenshots of the platform, but I will actually do a demo in the platform in a minute. But you have, as you say, a very interactive way to visualize your data. You can have customized plots that you just create for yourself, for your specific case, let's say. It's easier to explore. You can see the uncertainty as well in your predictions. And once you've finished your piece of work, as I say, it's easy to share through dashboards. So here, for instance, you have a nice, simple dashboard that you can share with a colleague to show him your results. So now I'll spend the next couple of minutes in the platform. So hopefully you can all see this. We are now in the platform. This is the folder where we developed the use case I'm going to present in a minute. But before that, just want to introduce you to the platform. So you can create notebooks, different folders. So here I just started a notebook that I called my new demo, where I loaded some data. So just before I showed you the workflow where you can import data, explore, transform, model, and predict. So I'm going to go through it quite quickly, just with this simple demonstration. So to explore the data, we have all the typical plots to understand the distribution of your data, the relationship between them. I'll just show one more here, where you can select the data you want to look at, the different columns. So here, one of the advantages as well is that this is, we call that a no-code environment. So you don't need to know how to code in Python, for instance, to use this, this tool. You just need to know your data in a way, and that's enough. So here, for instance, we have a way to visualize the relationship between the drag of a spoiler and the different parts, the different, let's say, parameters of design, and is really kind of interactive. You can see, for instance, if I want a good drag and a good lift, it gives me a lot of insight on, okay, apparently I need to have a high width, a high value of the chord. So just by exploring your data in a very interactive way, you can already get a lot of insight even before creating a model in the platform. But then once you've explored your data and transformed them, you can create models. So here we have a variety of models as well. I will just show an example with a neural network where I can decide what are the inputs that should be in my model. So I know, for instance, I need the width, the chord, the NACA, the alpha, and I want to predict the drag and maybe the lift as well. And here I'll train a very quick model just to show you how it works. I can decide to have uncertainty in my predictions as well. So when I get a result, the model will also tell me how sure it is of itself about that result. So it helps me making my decision. So here the model trains really quickly. It's a really simple model in a way. But then once this model is trained, I can then use it to make predictions. So here, for instance, I can make a prediction of my drag and my lift that I just learned. And here the idea is that I can now, with these sliders, change my input parameters and have an outcome of what the drag and the lift would be. So the data that I loaded are from simulation that took some time to produce. And so if I want, for instance, to know what would happen if my width would be higher, I would have to change the design, remesh, rerun the simulation, post-process the result, and calculate the drag. And now what I can just do is use my model, change the value here of the width or the chord, and have a like real-time answer of what would be the impact. And so I can see here, for instance, I want my lift to be reduced. Okay, so it looks like changing the value of the chord will do this, and I can quantify it in a way. One last example that I'll show you is curve prediction as well. If you want to see the effect of the angle of attack, for instance, on my drag, can just do this, and here I'll have a curve. along with the uncertainty as well, which will be really helpful for me to know whether I can trust that result. And once I've done a notebook, so we call this a notebook, I can create a dashboard out of it and share it with other people. And today in the study that we've been doing with Kistler, we ended up with a few dashboards, which I'll be sharing with you. So I'm just going to jump back to the slides now. And I think we are going to start looking at the use case, which we called AI for virtual experiments. So we got provided by Kistler and a Kistler expert in engine combustion, Joël Henry, these 159 physical tests for engine calibration. So there are 159 tests where an engine was tested in different operating conditions. And so we got a big table with a lot of data, and I'm going to explain this table before I go more in detail. So what we have is, first of all, the operational inputs, which are the speed and the torque of the engine. So they're the two main parameters that we can play with to change the behavior of the engine. And then these operational inputs, once they're fixed and that we do the actual physical test on the engine, there are a lot of sensors that are put on within the engine to measure all these values. So you can see you have pressure values, temperature values in different parts of the engine. So these are measured from sensors. And finally, we have the outputs, which is the main quantities of interest. And you have, for instance, the power of the engine, but also the fuel consumption. And so with this data set, what we did was a few things. The first one is what we called a virtual experiment. So we trained the model to learn from this operational condition what would be the value of the sensor. So to do this, we created a notebook, as I showed just before, and I'm going to show you now the dashboard that kind of ended up at the end of the notebook. So I'll just go here. So here, this is a notebook where we have trained the model to predict from these operating conditions what the sensor values would be. And that means that now if I want to, let's say, know what would happen if I had a higher engine speed, I can just change the value here, and I can see all these sensor values or virtual sensor in a way changing. So I can understand, okay, if I reduce my value, how is my HRCA 50 affected? And you can see it's greatly affected. And now if I change the torque value, is the effect as big? And that enables to get some insight without having to go to the lab and perform the actual experiment. You can also plot curves, as I showed. Here we have a nice plot, which is a sensitivity sort of study, where you can see all the different sensors and how they are impacted by our two inputs, the speed and the torque. And you can see the more it is red, the more it has an impact. So you can see that the torque has a lot of impact on most of the sensors, while the speed doesn't. And the speed maybe has a strong impact on this one, for instance. So these are the kind of insights you can get by performing virtual experiments. And then you can see, for instance, okay, if my speed is really low, what happens to the air pressure at the outlet of the compressor, for instance. So this is performing virtual experiment, and you can already bring a lot of insight very quickly. Now, the second thing we can do is to look, and again, it's virtual, but it's an impact analysis between the sensors and the outputs. So now we trained another model where the inputs this time are the sensor values. And we predict the main outputs, which are the power or the fuel consumption. So I'll go back in here, show you the next dashboard. So you can see it's a similar layout, but now this time I have way more parameters. They are all my sensor values, and I can change them to see what would be the effect on my main inputs. So for instance, I can change the pressure of the air in the compressor, and you will see that there's a very small effect in a way on my outputs. I can change another parameter, and here, for instance, we'll see the effect seems to be stronger. If we look at BSFC, for instance, there's a big effect. So here, that helps me to link the values of my sensors to what would be the power or the fuel consumption in my engine. Yeah, so the last thing we did was to, and we call that boosting existing data. So the idea is we have a data set of around 150, 160 experiments that were carried out. And now what we do is, if we have a question about how would the engine have behaved if we had done this test instead, or if we could do this test. And so what we do is we make these changes and rerun all these tests to understand what the difference is. So that will help us answer a few questions, and that is the questions we're going to look at now. So the first question we looked at was, what would happen to the fuel consumption if I had done all my tests with a slightly earlier combustion? So when you have your cycle, combustion cycle, if we had done, for instance, the combustion just 1 degree earlier, what would have happened? The second use case is whether it would be worth to reduce the charging loss by 5%, and I'll explain a bit more later. And finally, the last one is about what is the effect of the intercooler? Does it have a big effect on that, on the fuel consumption? And we can see that we can answer those by changing the sensor values and looking at the impact on the output. So for the first one, what we did was to take all the existing data and change the time of combustion in a way and make it 1 degree earlier. And then we looked at what would be the new fuel consumption, and we compared it to the original one. So we have, and I'll again jump back in the platform, first dashboard here that shows this, what's called a shell graph, where you have the speed of the engine, the torque of the engine, and then here the z-axis, and the color as well is the ratio of the brake-specific fuel consumption. So that's an indicator of how much fuel you consume, and it's the ratio between my original data and my new data when I have the combustion slightly earlier. So if you have a value of 1, it means that an earlier combustion doesn't have an effect on the fuel consumption. If you have a value above 1, it means that you will actually have a higher fuel consumption, and below 1 means a lower fuel consumption. So here, by looking at this shell graph as well, with the colors, you can see that at low values of the engine speed and low values of the torque, if you have a combustion that is slightly earlier, the fuel consumption will be higher, you're above 1. But if you have a high speed, for instance, in your engine and a low torque, you can see that the fuel consumption will decrease. And you see here, you might have, for instance, 2% decrease if you look at this ratio of before and after. And here you have a similar plot, but viewed from the side, so it might be a bit easier to look at. And you can see, for instance, that if you look at the value of HRCA 50, for low values, it might not make a big difference, and you might actually end up consuming more fuel. But for average values, you can reduce by 1 or up to 2% if you look at the trend, the fuel consumption. So if I go back here to the slide to summarize this one, let's say for high or for low value of the speed and low value of the torque, the fact that being a bit earlier produces a higher fuel consumption means that this part of the operating condition is already well calibrated. We cannot make it better. Then for low values of the, or high values of the torque, it looks like the ratio would remain around 1. We might gain maybe up to 0.5%, but not much. But for low values of the torque at high speed, it looks like this place could be improved by an earlier combustion by up to 1 or 2%. So that's the kind of insight the model can give you. Now, if you look at the second use case, here we want to know whether it's worth it to reduce the charging loss. So in the charging cycle, we have the valves that will be used to kind of get rid of the exhaust gas and suck in the new gas. And this will create charging loss due to the geometry of the valve, the friction of the air as it gets out of the combustion chamber. And the question is, if I could reduce this by 5%, would it be worth it? Would it reduce my fuel consumption or not? And that's a hard question, because most of the time we cannot know ahead of time. We have to try. And the problem is that this kind of improvement is not really easy. It's not cheap. It's not a 5,000 euros problem. It will be a lot of time, a lot of money to try to improve this charging loss. It might be by changing the valve timing. might be by changing the coating, and that might be really expensive. And by the end, you might realize that it doesn't affect at all your fuel consumption. So here the idea was, could we use the AI to know ahead of time, quantify what would be the effect of reducing the charging loss? So again, I'll go back to the platform, showing similar graphs. So here you can see a similar graph. We look again at the ratio. If we're below 1, it means that there would be a gain in fuel consumption. And it's quite interesting. You can see, for instance, that at low speed, there's no gain. You remain around 1 here. But as soon as you reach higher values of the speed, and especially for an average torque, you can get a decrease in the fuel consumption by up to 1%. And you can see it here again. You can go down to nearly 1%, or let's say around 0.5%. And then that will help the engineer make the decision on whether this is worth it. So if we look here, as I just said, no gain for low values of the speed, but for high values of the speed, average torque, we can gain up to 0.5%. And here I was discussing with the Kistler expert who said that these agree with the fact that it's a diesel engine, but 0.5% could still be worth it. And that's what's important, is that this 0.5% is the value that the engineer would need to take their decision. And currently they cannot have it, but with this kind of models, they can be informed and make the right decision faster. And for instance, if the gain was 0.1%, maybe it wouldn't be worth trying to improve this. Finally, the last use case is about the effect of the intercooler. So whether removing the intercooler has an effect on the fuel consumption. And again, maybe we might understand it qualitatively. We might understand that if there's no intercooler, the air will be warmer and maybe less dense in oxygen. So maybe the fuel will increase, but we don't know by how much. We don't know if that's true. So again, in the platform, we ran all the experiments virtually by kind of considering that the intercooler wasn't there. So we changed the sensor values to account for that. And this is the shell graph that we got. So you can see here quite an interesting trend where for values of the speed of around 2000 RPM and high torque values, we have a very kind of high and distinctive increase in fuel consumption. You can see it here as well, around 2000 RPM. We have an increase in the fuel that is more than 10%. So you see 1.1 is 10% increase. So here we have 10 to 12% increase in the fuel consumption in this area. And you can see in the other areas, we're actually going back down to around 1, which means that the effect is smaller, but we have a really big increase there. And again, talking to the expert from Kistler, he said that this makes sense because if we don't have the intercooler, the temperature is higher, and so there's a smaller density of oxygen, and so the efficiency goes down, especially in the best operating condition, best operating area of the engine, which is around this 2000 RPM. So it makes sense that the efficiency goes down there, and because the efficiency goes down, the fuel consumption will increase around here. So this result makes sense to the expert, but the extra thing that they bring is the actual value. So now we know that it's around 10, 12%. We could guess that it would increase, but now we know by how much. So again, this is really helpful to put numbers on questions we have before we act, so we can ensure we take the best decisions. So now the last slide, I guess, is to show you how you can then combine all these results in one bigger dashboard, for instance. So if, let's say, you have to do this study and share that with your colleague or your boss or someone else, another department, you can just share this dashboard with them, and then they can interact with it themselves. It's not just one plot. They can see how it works. They can look in the notebooks how you made these plots. So as I say, you can share with colleagues. We have some clients who share with their own clients as well. They find it beneficial for their clients to be able to access this kind of dashboard. So that brings me to the end of my presentation. Thank you for your attention. And If you have any question, please feel free to ask. Thank you.